Why do you feel lighter when you go underwater? And why do some things float? Well, this has to do with something called the buoyant force. And in this video, I'm going to try to explain to you how that works. So let's consider this situation here. We've got a beaker of some sort of fluid, and inside we've got some little cube. It's L by L by L, so that's its volume. And what I want to talk about is the difference between the pressure of the fluid at the top of the cube and at the bottom of the cube. So let's go into that. As I showed in a previous video, the pressure in a fluid depends on the depth. So the pressure at the top of this little cube of whatever it is, whether it's wood or metal or something like that, pressure at the top has to do with the atmospheric pressure at the very top of the fluid, so that's atmospheric pressure, plus the depth, so rho GH. So that's H down from the top of the surface all the way down to where the top of the cube is. So this is the density of water times 9.8 meters per second squared times that H. Now, the pressure at the bottom of the cube is going to be slightly different because it's a little bit deeper in the fluid. It's deeper by the amount of L. And so now if I want to figure out the pressure at the bottom, it's going to be atmospheric pressure plus rho G. Now, instead of times H, it's going to be H plus L. So H is the distance from the top of the fluid to the top of the cube, and then plus L is all the way down to the bottom of the cube. So it's slightly deeper, so it's going to have slightly more pressure. Well, with that slightly increased pressure, what that means is that you're going to have a difference in pressure between the top and the bottom of the cube. That difference in pressure can be explained by this, pressure bottom minus pressure top. And so I just take these terms, and I subtract them. All right, here's the pressure at the bottom, here's the pressure at the top. And you can see that a number of terms are going to cancel, like the atmospheric pressure term, that'll cancel, and then rho times G times H will cancel here. But what we'll be left with is this, rho times G times L. So that's the extra depth that this cube has in the fluid at the bottom surface of it. So this change in pressure, the difference in pressure between the bottom and the top, is given by this. Now, we can translate that into a force to try to figure out what the buoyant force is. If we remember that pressure is just force divided by area. So that's this thing here, okay? So pressure times area is going to give us a force because the areas will cancel, okay? So let's figure out what the force is that's going to be lifting this cube up that makes you feel lighter when you're underwater. That's the buoyant force. We'll calculate what it is here, okay? So what we do is we say, all right, that force is equal to rho times G times L times an area. Well, that force is acting on the bottom of the cube, and the area of that cube, its face, is just L squared. So now I say rho times G times L squared. Well, that's going to be rho times G times L cubed. So what that tells us is it's L cubed is actually the volume of this little cube. So it's rho, the density of water, times G, 9.8 meters per second squared, times the volume of the cube. And so what we can say is that the buoyant force of any object that is placed in water is equal to the density of water, not the density of the object, but the density of water times gravity, 9.8 meters per second, times the volume that is displaced by that object. So this difference in pressure between the bottom of the cube and the top of the cube is what results in the buoyant force. So I say everything is going to have a buoyant force, even if it sinks. So that might lead to this question. If everything has a buoyant force, then why do some things float and other things sink? Well, let's take a look at this. Imagine we've got an object here, and it's just barely floating. And by that, what I mean is that the top surface of this object is just touching the water, okay? So it's not like even an ice cube, which is barely above the water. It's just level with the water, okay? So this thing's barely floating. And then let's say we've got another cube of equal volume, and it's made out of lead. And it, of course, sinks to the bottom of the beaker. So why is one thing floating and the other thing sunk at the bottom if they both experience the same buoyant force? They should have exactly the same buoyant force because, remember, it only depends on the volume of the object. So if they both have exactly the same volume, and G is the same for both of them, and the density of water is the same for both of them, then they should both experience the same buoyant force. And the answer is they do both experience the same buoyant force, but we also have to take into consideration the weight of the object. So let's take a look at the first one, the one that's just barely floating. So it has a buoyant force equal to the density of water times G times its volume. So every object has a buoyant force equal to the volume of water it displaces. If you were to take that volume and weigh it, that weight is exactly equal to the buoyant force. So This is the volume of water that it's displacing, and multiply that by g to get its weight. That's its upward buoyant force. And it exactly equals mg pulling down. So these things are balanced, and that's why this guy is just barely floating like that. So we have a force diagram saying that they're balanced like this. But what about the case for lead? Well, in lead, it experiences exactly the same buoyant force, right? This is the same because it's got the same volume. But mg is just a whole lot greater because lead has more mass in it for a given volume. It's got greater density, and so this thing sinks. That's why it sinks. So this is the idea. This is why the buoyant force acts equally on all objects of the same volume. The amount of water that they displace, the weight of that is exactly equal to the buoyant force. But some things just have more weight. And if they have more weight, they're going to sink to the bottom. And things for which the buoyant force is roughly equal to the weight, those things will just barely float. And if we have actually something that's less dense than water, then it will pop up above the surface. And that's the case of ice that I've talked about in other videos. Hopefully this is helpful and it can explain some questions you have about where the buoyant force arises from and what's the difference between objects that do float and objects that sink.